Hello, I'm Matt Helmers with Iowa State University Extension and Outreach, the Department of Agricultural and Biosystems Engineering, and the Director of the Iowa Nutrient Research Center. Really happy today to talk to you a little bit about the 4 R's of nitrogen management for nitrate leaching and crop production. So we're going to try to go through why we're worried about nitrate leaching, some of the causes of it, and then what some of our management practices might be able to do for us in reducing nitrate leaching, and then how they might also help us with crop production. As we think about the 4 R's, we're thinking of the right source, rate, time, and place of nitrogen management in this case. So why are we concerned about nitrate loss? I think we need to start there as we think about nitrate leaching, why are we concerned about it? I would say first and foremost, one of the reasons is that nitrogen that's lost in the nitrate form below our plant root zone is a loss of a resource that's needed or aids in crop production. Specifically in Iowa, that would be corn production, because the corn is the crop that we fertilize. Then another reason, if certainly at the field scale, we're concerned about that loss of a resource. But then, so we think downstream from that, local drinking water concerns. And that may be in small private wells. There are a number of private wells in Iowa that would test high in nitrate. Regional drinking water supplies, whether that be rural water or other small municipalities that might have high nitrate levels in their water. Or larger municipalities like Des Moines, like Cedar Rapids, where they may be concerned about being able to supply water to their customers that meets the drinking water standard. And the drinking water standard for nitrate nitrogen is 10 milligrams per liter or parts per million of nitrate nitrogen. Now one might say, okay, why are we concerned about that? Matt's mentioning these drinking water concerns. There's some health concerns related to nitrate nitrogen, specifically blue baby syndrome, and then there's some other emerging concerns as well. And so, it is a concern from a drinking water resource standpoint. And I would say from at the local level, whether it be a private well, to maybe on a larger state scale, where we're talking about some of our larger municipalities. Then there's also regional or national water quality concerns. And what I'm thinking about here is the hypoxic zone in the Gulf of Mexico. We'll talk about that. Really, that Gulf of Mexico hypoxia is what led to the Iowa nutrient reduction strategy. So in 2008, the Hypoxia Task Force developed an action plan and called for states to develop state-level strategies for reducing nutrient loading down the Mississippi River to the Gulf of Mexico. And the goal of the Hypoxia Action Plan is to reduce the size of that hypoxic zone to 5,000 square kilometers. So just to back up, Gulf of Mexico hypoxia, there's a zone in the Gulf that most summers, really each summer, we get a zone that is so low in dissolved oxygen that it doesn't support aquatic life. They attribute the growth and the size of that zone to nitrogen and phosphorus loading down the river. That promotes algae production. When that algae dies and decomposes, it consumes that oxygen. And so we have that zone with low dissolved oxygen. So the black line on this graph here, this is a few years old, but really illustrates that black line is what the task force goal is to reduce the size of that zone to about 5,000 square kilometers, which, if I'm not mistaken, is about the size of Rhode Island. You'll notice there the blue line is our long-term average, which is about 13 to 14,000 square kilometers, about the size of New Jersey. So 2 to 3 times larger in size than the goal. So there was a science advisory board that released a report, EPA Science Advisory Board. Actually, some members of the Iowa State University faculty were on this science advisory board. That recommendation was to reach that goal of 5,000 square kilometers, we needed to reduce total riverine nitrogen and phosphorus loads by 45%. And so that's really what the goal is for a load reduction of nitrogen and phosphorus down the river. And as we think about nitrogen, most of the nitrogen that we see in the streams will be in the nitrate form, certainly from the state of Iowa. So as we think about this, we're really trying to look at about a 45% reduction in nitrate loading from the state of Iowa. Okay, and so there's been some work. This graph actually is in the Iowa Nutrient Reduction Strategy annual report. But there's been work in Iowa going back a number of years that monitors nitrate nitrogen load leaving the state and looking at what's leaving from our major rivers to estimate the load loss at a statewide scale. And so this dates back from 2000. And so you'll notice here the triangles that are in red are the nitrate nitrogen load, and then the flow is the blue diamonds. And so you'll kind of notice that in that 2000 to 2007 or 2006 period, if you were to draw a line through that, that's a pretty flat line, and it might be somewhere around 175 to 200,000 tons of nitrate nitrogen load leaving the state. If you look at 2007 to 2017 in this case, and just were to draw a straight line through that would be up closer to 350 to maybe 400,000 tons per year. If we just look at those red triangles, 350,000 as I look at that now. Okay, so we went from like 175 to 350,000. One might say, oh, we've had an increase in load, and I think we have. But we have to look at maybe what's a cause of that, a primary cause of that. And as we look then at relating the nitrate nitrogen load to the flow, one of the things you'll notice is that there are 6 years that have a flow of greater than 30 centimeters or about 12 inches. Should have the right units there, but about 12 inches. Okay, that have greater than that 12 inches of flow. And what you'll notice is all of those years are 2007 or later. So as we looked at that 2000 to 2006 period, there was a lot more what we would say are lower flow, or at least below that 12-inch range, whereas after that we saw higher flows. And you'll notice here that if you were to draw a regression line through there or a straight line through there, there'd be a pretty strong correlation between nitrate nitrogen load and the flow that we see leaving the state of Iowa. So, if we could just have lower flow years, we would see less nitrate nitrogen load leaving the state. I think a good example is the lowest load that we see on there is in 2012. Most folks will probably remember that was a very dry year in the state of Iowa. Don't have the load yet for 2021, but that was also a pretty darn dry year through much of Iowa. And so we're probably going to would expect to see a low nitrate nitrogen load for 2021 as well. So I think as we think about nitrate nitrogen load, there's some infield management practices and edge of field practices that we can implement to reduce nitrate that gets to our stream. But we have to recognize at least a big driver in kind of the overall load that we see leaving the state is how much precipitation we get. But that does not mean that there's not anything we can do about it, because we're going to talk about some of the management practices we may be able to use to help us in reducing nitrate nitrogen loading that leaves our plant root zone and ultimately leaves the state of Iowa in our waters or gets to that shallow groundwater. Okay, so let's think back to what's happened in Iowa. And I think the next couple slides to me really illustrate why we have some of the challenges that we do with nitrate nitrogen in the state. So this is looking at land use divided up into, in this case, 3 categories and then a combined, but categories of corn, soybeans, and oats. And then the triangle, purple triangle at the top is the combination of corn and soybeans and oats. I really like this graph Because sometimes I've heard that people say with biofuels in Iowa, we've seen an exponential increase in corn acreage. Or I've heard people say, well, in the late 2000s, about 2010, somewhere in there, Iowa's become a continuous corn state. Well, if we look at that the red circles, the one right in the middle, we've grown anywhere from 10 to 14 million acres of corn annually in the state of Iowa, dating back 100 years. So this goes back to the early 1920s. So we've grown between 10 and 14 million acres of corn consistently over the last 100 years. So we don't see this exponential increase in corn acres in the last 20 years. It's really, Iowa has grown a lot of corn. But what has happened is, if we look at that second line with the circles, you'll notice that one is increasing. And I bet I could have not even put a legend on there, and most everybody would know what I'm talking about if we're thinking about what crop has increased over the last 100 years. And that's soybeans. We went in the 1920s, hardly any soybeans. Now we have, in some years, 10 million acres of soybeans. So what have those soybeans displaced? Things like oats. So, in the 20s and 30s, 40s, even up until almost the late 50s, we saw about 6 million acres of oats grown in Iowa. But then you've seen a steady decline throughout that period. Some if you're looking really closely at that graph, might be interested to see those spikes in oats in the 1980s, and those also correspond with a decrease in corn during that period. Some people may remember the PIC, or Payment in Kind program, that paid farmers to reduce their corn acres during that period, and many planted to oats. Okay, so we have replaced small grains. If we were to look at hay ground, pasture ground, we'd also see a decline, since the 1920s, 30s, and 40s. So we've displaced a more diverse cropping system with a more annual cropping system that tends to grow during the same time of the year. Corn and soybeans growing in the same time of the year. Now, why might that be a problem? Okay, this is a slide that a colleague here at Iowa State University, Dr. Mike Castellano, put together that I think really highlights why we have some of the problems that we do in Iowa, and why some of the changes in land use may have exacerbated this problem. So as we look at this red line would be the kind of estimated rate of soil nitrate production from native soil organic matter. So we have very organic rich soils in Iowa. That's one reason why we have the tremendous crop production that we do. But when those soils get warm and moist in the spring of the year, we can convert a portion of that stable organic nitrogen pool into the nitrate form. Okay, so then it's in the soil, in the nitrate form. Then we have that green line, which illustrates the rate of corn or soybean nitrate uptake. So when that corn or soybean starts growing, starts taking up water, it's going to be taking up nitrogen with that. And so you'll see that that kind of peaks out in the midsummer. So if we look at that red line and the green line, you'll notice that they don't peak at the same time. They're not synchronized. Okay, so they're kind of asynchronous. Okay, that red peak and that period in the spring may be happening before we have a lot of active corn or soybean uptake of nitrogen. So, that wouldn't necessarily be a problem, right? But what happens in places like Iowa and a lot of the upper Midwest is during that March, April, May, early June period, before we get a lot of corn or soybean growth, we have that nitrate in the soil and we get excess precipitation. And that excess precipitation, infiltrates water into the soil, and the water in the soil may be greater than is the water holding capacity of the soil. So we leach we move water below the plant root zone, and when it moves below the plant root zone, we take nitrate nitrogen with it. So, if we could just not get that spring rain, we would greatly reduce some of our nitrate loss. But we do have that spring rain, excess precipitation. It can leach water and nitrate out of the plant root zone. But let's think about this as we think about those historic land use changes. If we were to have, we'll just say oats out there, a small grain, we may still have that red line that's similar, but that green line may shift so that there's more overlap, more synchronized timing in the spring of the year when that small grain like oat, wheat, may be taking up nutrients. Okay? Or what about if we had something like alfalfa out there, a forage? Again, that green line is probably going to overlap a lot closer with the red line. Another one, frequently have gotten questions about, what about if we had prairie out there? We have prairie that was natural in Iowa, part of the ecosystem, the tallgrass prairie ecosystem. What might that do? And I think that red line and that green line would probably match up pretty closely. Now, I don't have data to show you what the red line and the green line is, but we'll talk a little bit later about what we've found from nitrate leaching from things like cover crops, things like nitrogen management, but also something like prairie, where I think, as I just said, I think that red line and green line would match up pretty closely. Okay, and so as we look at this kind of across the region, and we think about this annual land use that we have out there, a colleague of mine, Dr. Bill Crumpton, put together this slide that I think really illustrates, as he looked at across the Upper Miss and Ohio River basins, and looked at what the flow-weighted nitrate nitrogen concentration was. That's the red circles, the solid circles, and related it to an assessment of what the percent cropland, so percent annual cropland was within those watersheds. So looked at the watershed level nitrate nitrogen load, the flow-weighted nitrate nitrogen, and compared it to the percent row crop, percent annual crop within that watershed. And you'll notice a pretty strong relationship there, R squared of 0.9, that as we increase the percent of annual row crop, the percent of cropland within a watershed, we see an increase in the flow-weighted nitrate nitrogen concentration. So I think, as we think back to what's happened over time in places like Iowa and a lot of the upper Midwest, is that we've increased within our watersheds the percent cropland as we've decreased maybe some of our forage ground, hay ground, pasture ground. We've increased our percent cropland. As a result, then increase some of our flow-weighted nitrate nitrogen concentrations that are leaving that watershed. So let's think, though, about how that nitrate makes its way to the stream. I think this is important. Sometimes I'll hear nitrate loss with surface or with runoff. Okay, with runoff, and our surface water runoff, so both slides here kind of illustrates the hydrologic cycle. We have precipitation, we have evapotranspiration, we have that what I would call direct surface water runoff. That arrow illustrating, going parallel to the land surface there. And that surface water runoff is going to be very low in nitrate nitrogen, might be 1 parts per million. Okay, versus what we see in water moving through the plant root zone, which might be 10 to 20 parts per million. So, direct surface water runoff nitrate loss is actually pretty low. Where we do get that loss is, you'll notice in both of these we have infiltration. So that's rainfall that falls on the land surface. It moves into the soil, okay? And then some of that is going to move deeper through deep percolation or laterally to the stream. Now, in the one on the left, we have a naturally well-drained soil. That infiltrating water is going to move below the plant root zone. It's going to carry some nitrate with it. And then that nitrate can make it to a downstream water body, whether that be a stream through lateral flow or to maybe a shallow aquifer through deep percolation. So that might be why we have high nitrate levels in some of our shallow groundwater and where it's a concern for drinking water wells. Now, the one on the right is the soil with poor natural drainage. Okay, and in those areas of the Midwest where we have soils with poor natural drainage, we implement that subsurface drainage system, that artificial subsurface drainage system, to lower that water table, to allow us to have some of that crop production. But that also takes in some of that infiltrating water and takes it directly to the stream, and so it delivers that nitrate, nitrogen, directly to the stream. So in both a naturally well-drained soil and soils with poor natural drainage, where we have that artificial subsurface drainage, we lose nitrate below the plant root zone. It's just that it's delivered to the stream in a different fashion. Okay? We'll have to acknowledge that that one on the right, where we have that artificial subsurface drainage, if it wasn't for that drainage, we would not be able to have the intensity of crop production that we do in many of those areas, because we would have waterlogged soils and would not be able to have some of the crop production there. Okay, so let's get into talking about some of our work, looking at the impact of nitrogen management, cover crops, manure management on nitrate and crop production. And so with my group, we monitor a number of subsurface drainage facilities throughout the state of Iowa. And we do this in a similar fashion. We will have a plot where there are tiles on either edge of the plot, and then there'll be a tile line down the center of that plot. And we monitor the flow and collect water samples from that center of that plot. So we assume that that plot area, or the area that we're collecting drainage from, is essentially the middle half of that plot. So midway between the border tiles on either edge that we have there. Okay, and so that tile line from an individual center part of the plot dumps into one of our monitoring sumps. And so you can see there that black sump, garden variety sump like you might have in the basement of your house. Certainly in central Iowa, we have a lot of those. Okay, so the tile line's going to drain directly into that sump. There's a sump pump in there. It's going to pump it out. We have a flow meter in line so that we record how much flow is being pumped out, and then we can accumulate that on a daily or weekly or monthly basis to say how much water flow exited that drain for that individual plot. Okay, that gives us the volume of water, but we also want to know the quality of that water. And the way we monitor here allows us, we have an orifice in line in this pipe, and the back pressure forces a small portion of all that water into a sample container. So the great part about that is that if we get more flow, we get a little more water. So we can collect a flow proportional water sample. So we can have a good idea to get a representative water sample for all of that flow that was pumped out. And having a flow proportional water sample is important because we want to get more representative sample when we have more flow, because that's having a greater contribution to the load that's exiting downstream. Okay, so this shows you drone footage of the site up in northwest Iowa near Sutherland, so the Northwest Research Farm Association up there, 32 plots at this site. And this is what those sumps look like out in the field, and the crew up there will go and collect water samples 1 to 2 times a week, depending on the flow, and record how much flow has been coming out of these. You'll notice some antennas there at this site and a couple of our other sites. We have the flow meters are hooked into data loggers, so we can get a lot shorter time period flow estimations, can definitely estimate it on a daily basis. Okay, so we're going to do a quick tour, a virtual tour of 4 of the sites that we do replicated drainage plot research. And we're going to start at our Gilmore City Drainage Research Facility in the heart of north central Iowa, up near Gilmore City in Pocahontas. And this site, the the broad we, because my predecessors in the Department of Ag and Biosystems Engineering really did a lot of this work for the first 15 or so years. We monitored drainage water quality at this site since 1990. So they put the drains in 1988. There was no flow in 1989. And then we've been monitoring continuously over that period. So this is a really unique data set of having, in this slide, a 30-year summary. And what I think is important, and many of you that have heard me talk, you've probably seen this graph more times than you want, for sure. More times than you want, without a doubt, okay? But I think it's that important. So this slide is the drainage, the flow-weighted annual nitrate-nitrogen concentration, and the nitrate-nitrogen loss from our drainage system at Gilmore City from a combined corn-soybean cropping system where we had about the same nitrogen management those whole 30 years. Early spring side dress at between 150 and 160 pounds of nitrogen per acre, total nitrogen application, okay? And what you'll see that the squares, the green line shows our annual drainage. And like, anybody that's lived in Iowa or worked in Iowa, been in the upper Midwest, that amount of drainage, that amount of water flow below the plant root zone is going to vary year to year because our precipitation varies year to year. So we have a high of about 27 inches of drainage in 1993. That was a flood year throughout much of the state of Iowa and certainly in north central Iowa. But then the next year, only about 2 inches of drainage, okay? So on average, over that 30 years, we got about 10 to 12 inches of drainage, okay? That ended up with a nitrate-nitrogen loss of about 35 pounds of nitrate-nitrogen per acre per year from that combined corn-soybean cropping system. And at this site and some of the others I'll show you, we lose about the same amount of nitrogen in the corn year as the soybean year. Okay. Other thing that's important here is look at that nitrate-nitrogen concentration. Okay, so it was dry in the late 80s. We saw a lot of drainage in the early 90s. You saw that flow-weighted annual nitrate-nitrogen concentration go down to a low of about 7. Okay, we talked earlier, drinking water standard of 10. If we had just looked at the nitrate-nitrogen concentration in 1992, 93, 94, those are below 10 parts per million, we're pretty good with this management. But that was probably because it was wet years that flushed the profile out. We had a number of dry years, and you'll see then from 95 up till 98, 99, that nitrate concentration is increasing, and so now we're about 20 parts per million in the drainage water. So, we can have a low of 7 or then a high in 2013 of about 21, all from the same management. So this would be a management that we would say is pretty close to a, best management practice, and we still would be challenged to meet that drinking water standard of 10 parts per million consistently with this system. It also, if we look at 2012 versus 2013, so 2013 is where we had the highest nitrate concentration. Hopefully you can see that blue one, that kind of spike that we see there later in the time series. That's 2013. 2012, you remember, very dry, so we lost hardly any nitrate. But then when we got that rainfall in 2013, we saw that spike in nitrate concentration. That's important and I think relevant to things today. We've had couple dry years in a row in many areas of Iowa. I think we could expect when we ultimately get drainage, we're going to see some high nitrate coming out of those systems. It's maybe a little late now, but in the future, when we might have these types of situations, I think that's why something like a cover crop may be very important, because it may help us take up some of that residual nitrate that's in the profile. Now, for example, in 2013, one of the highest nitrate concentrations we saw at this site were from plots that were in soybeans in 2013. So it wasn't because of nitrogen management for crop year 2013, it was really, more of a carryover from 2012. So there wouldn't have been much we could do with nitrogen management, preceding that soybean crop, but something like a cover crop might help us. And that's where we'll go here in a minute. So as we think about the 4 R's, I would say the biggest R's is the rate. Okay, and so thinking about what's the nitrogen application rate that maybe can provide the greatest crop production while minimizing the risk of nitrate loss. And so this is looking at all the data that we have for our Gilmore City site, and you can see as we increase nitrogen application rate that nitrate-nitrogen concentration increases. A couple things though. Even when we apply no nitrogen, we still see about 7 to 8 parts per million of nitrate-nitrogen in our tile line. And this gets back to that red line, green line that we saw in the nitrate production from native soil organic matter, and then the uptake from the crop. So these great soils that we have, even when we apply no nitrogen, we still see some nitrate coming out of the system. The other thing is this line is not linear. So as you get above 150, you'll notice that curve really starts to increase. And so if we have, application above really what the crop may need to optimize crop production, we may see a pretty big increase in the risk of losing that nitrate. You can see here, if we were to extend that, when we applied about 250 pounds of nitrate-nitrogen there, that nitrate concentration might be up 25 to 30 parts per million versus, at 150, it's about 13 parts per million. So really thinking about that nitrogen application rate is critical, and I think something we need to do even more of in the future, because it does have if we are applying nitrogen above what the crop needs, that's a cost that we're not getting a return on, and there's a environmental risk there. So to me, making sure we're putting on the right nitrogen application rate, that R of rate, has the potential to improve the profitability for farmers, as well as reduce some of the potential environmental impact from this system. Okay, so what are some of the other practices we might be able to use? Now tillage is not a 4R, I recognize that, but we do get a lot of questions. How could tillage help us with nitrate loss? And using no-till provides us tremendous benefits from a soil health standpoint, soil erosion standpoint, phosphorus loss with runoff, but the research that's been conducted would indicate maybe less potential for no-till to reduce nitrate loss. We studied this at a couple sites, but I think this one kind of illustrates it pretty well. Somewhat not what we expected. So at this site, we went to no-till in 2010. So this first phase, that first kind of time block, 2011 through 2015, the circles are conventional till, the squares are no-till, nitrate load. And so what we saw that first 5 years of implementing no-till, at this site, we saw a decrease in nitrate loss with that no-till, about 72 pounds per acre cumulative over that 5-year period. If we look at the next 5-year period, we saw only about a 13 pound per acre cumulative impact of that no-till. So a lot less impact. I think as we move further out with that no-till, as we get some of the soil biological changes, we probably see a less difference between the no-till and the conventional till. So as we think about nitrate reduction, I don't think we can rely on reduced tillage to do a lot for us there. Again, we still need to do that for all kinds of other reasons, but can't be relied on for nitrate reduction. Okay, but there are some things we can do in field. Cover crops, great example. So this is looking at a winter cereal rye cover crop, first 5 years and second 5 years. Both cases, this is where we had some tillage, both without cover crop and then with. So the red circle is the conventional tillage nitrate load. The upside down triangle, the green, is conventional tillage with rye cover crop nitrate load. So First 5-year period, we lost about 75 pounds per acre cumulative less where we had cover crop. Second 5-year period, about 35 pounds less. So all told, over a 10-year period, we lost about 111 pounds less nitrate nitrogen where we used a winter cereal rye cover crop. You know, if you just say that average, that's about 10 to 11 pounds per acre per year less nitrate nitrogen loss where we have a winter cereal rye cover crop. And this was grown in north central Iowa where we don't get the best cover crop growth. So I think this is really important and useful information. We also looked at cover crop impacts when we have no-till. Okay, so the first 5-year period, only 3.6 pound per acre difference cumulative between no-till with no cover crop, the squares, the triangles, then no-till with cover crop. Okay, so that period, I think we have a lot of probably soil biological changes in both systems. Didn't see much impact. But boy, look at that second 5-year period from 2016 through 2020, 45 pound per acre cumulative less nitrate nitrogen loss where we had the cover crop. Okay, again, almost to that 10 pound per acre per year reduction in nitrate nitrogen loss when we have that cover crop. So this cover crops might be the plus that we add to 4Rs. The plus is something like cover crops can help us reduce some of that nitrate nitrogen loss. And a way that I think it's doing that is we think back to that red line and the green line. We're reducing some of that gray area in the spring and in the fall of the year when we don't have anything growing with our annual crop. Okay, let's move to the Northwest Farm Association near Sutherland, Iowa. Okay, and so we've been looking at the impact of different nitrogen timing treatments. So as we think about the right time of nitrogen application, we have a fall anhydrous, treatment 1 with inhibitor, spring pre-plant anhydrous, split application. So we have 40 pounds of urea as starter plus in-season Agritrain treated urea. All of those have a total nitrogen application rate of 135 pounds of N per acre, which is about the MRTN when we started, the maximum return to nitrogen when we started this. We also have a no nitrogen application treatment. Okay, so we started the study, the treatments in 2015. 2013 was the last time there was any nitrogen applied on these plots, and that was where there were oats on the plots to look at the drainage, to put the drainage in, that year. And so just a little nitrogen for those oats. So we're going on many years of no nitrogen application at this site for treatment 4. Okay, so this is looking at the flow-weighted nitrate nitrogen concentration averaged for 2015 through 2020. Looking at the top graph is the corn phase of the system. The bottom graph is the soybean phase, okay? And then we have fall, spring, split N, and no N. A couple things to note here. Remember I talked before about similar nitrate nitrogen concentrations in the corn year as the soybean year, even though soybean gets no nitrogen, at least external inputs of nitrogen. And you'll notice, we saw about 10 parts per million from the fall N or spring N in the corn phase. We saw about 11 parts per million fall N, spring N in the soybean phase. So similar nitrate nitrogen concentration in the corn year as the soybean year. Okay. The next thing, fall N and spring N, we see no statistically significant difference in nitrate nitrogen concentration between fall N and spring N, both in the corn phase or the soybean phase. So obviously soybean phase, that's the follow on after, the nitrogen was applied to the corn. Okay. Now, this fall N was applied when soils were 50 degrees and cooling. And when we did that, we didn't see any difference in nitrate nitrogen concentration or loss compared to that spring N. There has been some work done previously by Giles Randall and Jeff Vetch in southern Minnesota where they did see some some increased nitrate-nitrogen concentration with that fall N. But it's very year dependent based on the type of rainfall that we get, type of temperature conditions. But over this period from 2015 to 2020, we did not see a difference in nitrate-nitrogen concentration between fall N and spring N. But we did see a reduction when we used a split nitrogen application, some pre-plant or some at planting, and then side dress. We saw maybe about a 20% nitrate-nitrogen reduction when we compare, say, spring or fall N to that split N. So you'll see that letter B above that in comparison to the fall or spring N, indicating if there's a different letter, it means there's a statistically significant difference at the P of 0.05 level. Okay, so we look at the no nitrogen, the one on the right in the purple, you'll notice lower nitrate-nitrogen concentration, and it was statistically significant in the soybean phase. But you'll notice, again, it's not zero. We're still seeing about 8 parts per million when we apply that no nitrogen, in that corn soybean system. So really kind of illustrating one of our big problems is that we have this annual cropping system out there that isn't growing a great percentage of the year. So even when we apply no nitrogen, there's some risk of nitrate loss. As we combine across the corn soybean cropping system, again, no difference between fall and spring N. Split N, we do see reduced nitrate-nitrogen concentration compared to the fall or spring, and then the no N, again, the lowest of all those treatments, but again, not zero, but really kind of illustrates maybe the maximum nitrate reduction we could get with just infield nitrogen management. And so we're talking about kind of 25 to 30 to 40% reduction with no nitrogen application, at least compared to this spring and fall N, where we're applying close to the maximum return to nitrogen application rate. Okay, that's all fine and dandy. But what about the crop yield? Okay, so what we have, this is looking at the individual years of crop yield. And so the first bar in each year is the fall N. The second one is yellow, that's spring N. The third one is the split N. And then the last one, the green hash, is no nitrogen. Okay? As we look at it on average over those 6 years, there was no statistically significant difference between fall, spring, or split nitrogen. All of those were higher, statistically higher than when we applied no N. Okay? We would hope that's the case, because otherwise, why are we applying nitrogen if it doesn't really improve crop yield? You'll see, we had a low kind of increased yield with nitrogen inputs in 2015, about maybe 30, 40 bushel, whereas look at 2018, about 100 bushel yield benefit from that nitrogen application in that specific year. That was a wetter year, so we're probably getting greater yield benefit from that nitrogen in a wetter year. Okay. 5 of those 6 years, we saw no statistically significant difference between fall, spring, or split nitrogen application. Okay, so as we look at it, on average, no difference with nitrogen application, and in any of the individual years, only one of the 6 did we see a difference in corn yield with the different nitrogen management. And that was in 2017, where we saw a lower corn yield with the split N. Okay, so we applied that 40 pounds pre-plant, 95 in season. That went on about July 8th to 10th in that year. And we only had 1 inch of rain in the following month. So it was dribbled on or put down over the top, agrotane treated urea, and then we only got 1 inch of rain in that following month. I don't think that nitrogen got down to the corn root zone to really help us with crop production. So just something to think about as we think about, say, side dress application. We've actually, in the newer treatments that we started at this site in 2021, we're actually going with a higher rate, 80 to 100 pounds of nitrogen pre-plant, and then we will base that side dress application based on kind of weather conditions we've had and some of the modeling predictions of what we would need for additional nitrogen inputs based on work that Dr. Sotirios Arkantoulis is leading. So just something to think about, that in certain parts of Iowa with that late nitrogen application, we just want to be careful that we get it on at a period when we can hopefully get enough rainfall to move any of that nitrogen into the plant root zone. Okay, not the last. We got two sites in our virtual tour left today, okay? This one's quick. This is looking at a site, COBS. Now, what does COBS stand for? Comparison of biofuels. So this was started 2008 when we put the new drains in to look at different biomass production systems. So the four systems I'm going to talk to you today, this is a project really being led out of the Department of Agronomy with Dr. Matt Liebman and Dr. Michael Thompson. My group just helps with the water quality monitoring at this site. So four of the treatments that I think are important for this are, we have a continuous corn, we have continuous corn with cover crop, so kind of that 4R plus with the cover crop. And then if you remember back, 30 some minutes ago, you might not want to remember anything I said, but okay. I talked about what that prairie might do with that red line, green line, okay? And I told you I didn't have data for the red line and the green line, but I had data for what might be leached from that system, okay? So we have this continuous corn with cover crop, and then we have two prairie treatments. There were 24 plots at this site. There's 4 replicates per treatment. So in 2008, they seeded 8 prairie plots with the same seed mix. 4 of those have received nitrogen fertilizer, about 75 pounds of nitrogen per acre per year since then, and 4 of those did not. The fertilized prairie was to look at, did the fertilizer help us increase above ground herbaceous biomass? Okay, so this is looking at cumulative nitrate nitrogen loss from the drainage system for these 4 treatments. And what you'll see is when we have that continuous corn with cover crop, we reduce nitrate nitrogen loss from about a little over 140 pounds per acre cumulative down to about 110. So about a 30-pound reduction when we use that cover crop, even within a continuous corn system. Now, when we had prairie, we lost, from the 2 different prairies, we lost about 5 to 8 pounds of nitrogen per acre cumulative over that 10-year period from 2010 through the end of 2019. So, we had over 140 where we had continuous corn. We had 5 to 8 where we had the prairie, okay? And actually, on an absolute basis, a little less from the fertilized prairie. I think that no statistically significant difference there between prairie and fertilized prairie. There is between continuous corn with cover crops, and the prairie. But I think that fertilized prairie, we did increase above ground biomass production. So that may be one reason why we see, at least on an absolute basis, lower nitrate nitrogen loss from that fertilized prairie. But this really gets at, I think one of the biggest reasons why we have a nitrate problem. Yes, we can do a better job with nutrient management, and we have to do that, but we have to recognize that we have an annual cropping system where once there was a perennial, and that perennial did a pretty good job, even under, pretty good job of having very low nitrate loss below that root system of the prairie. We have to remember back when we applied no nitrogen to corn soybean cropping system, we were losing about 7 to 8 parts per million of nitrate nitrogen. As a point of comparison, the nitrate nitrogen concentration under that prairie and fertilized prairie is well below 1 part per million, down closer to 0.5 parts per million, and many times really close to the detection limit for the lab analysis of nitrate nitrogen. Okay, now on to the last site. And this is one that I think for anybody that's using manure, really maybe something to think about, and maybe an area that could help with crop production and maybe dramatic help with crop production and reduce some of the risk of nitrate nitrogen loss. So, many areas when we liquid swine manure, that may be applied early in the fall, as close after soybean harvest as possible because of logistical reasons. With research funded by the Iowa pork producers and calcium products, we looked at that early fall manure, that's the first bar, versus early fall manure, and then where we have a winter cereal rye cover crop, and then the late manure. Okay, so late manure would be after soils are 50 degrees and cooling. So this one shows the flow-weighted nitrate nitrogen concentration average from 2016 through 2019 for the top one corn phase, bottom one soybean phase. What we see here is that when we apply that manure early in the fall, we see higher nitrate nitrogen concentrations in the corn year, in that corn phase, statistically higher nitrate nitrogen concentrations. Okay, it's up about 20 parts per million versus 11 where we have early manure with cover crop, or about 14 where we have late manure. Okay, but if we did that early manure but we implement the cover crop, we can reduce that nitrate nitrogen concentration, at least compared to early manure without cover crop. So we can reduce the risk of increased nitrate nitrogen loss. And there's no statistically significant difference between early manure with cover crop and that late manure. Okay. Now, on the soybean phase, no difference due to the previous timing of nitrogen for the preceding corn crop, but where we have that cover crop implemented, so we're implementing the cover crop both in the corn phase and the soybean phase, we do see lower nitrate nitrogen concentrations. So as we think about this, if you could delay that manure application till a little later in the fall, when soils are 50 degrees and cooling, like I'd like to ask some folks is, would you apply commercial fertilizer early in the fall when the soils are really warm? And almost everybody says, oh, heck no. Okay, let's think about, could we do a little bit more of that with the late manure? Or if we have to do that early manure, can we get that cover crop on so we can reduce that risk of nitrate loss? Okay, now, but what about crop production? Maybe most important for the producer. Now let's look at what we saw for 3 years when we could really look at early fall manure in red, early fall manure with cover crops in blue, and then the green, that late fall manure. Okay, you'll notice in every year we see statistically higher corn yield where we apply that late fall manure. So this is, in all of these cases, the only nitrogen that's being applied is from that fall manure, whether it's early or late. The target application rate is about 150 pounds of nitrogen per acre per year. 3-year average corn yield benefit of about 40 bushel per acre when we apply that manure later in the fall. Okay, pretty substantial yield benefit. Okay, you'll notice there that first year we did take a little yield hit with the cover crops, but then subsequent to that, we've seen stable or in 2018 slightly higher corn yield where we had that early fall manure with cover crops. So as we look at that over the 3-year average, almost the same corn yield, whether it's early fall manure or early fall manure with cover crops, but in both cases less than where we late manure. So, maybe something to think about. Could we get a little more of that manure on later in the fall, get a little bit better nitrogen utilization from that, improve our profitability? I already showed you in the previous graph that helps us with reducing some of the nitrate loss. The other thing that we looked at this site is, what about spring manure application? Okay, I know there are some logistical reasons, understand logistical reasons why we do it early in the fall, but could we open up a little bit more window and put some on in the spring? Not all of it, understand, but maybe some. Okay, so again, 3 years of data. The blue bar there is spring manure. The green bar is that late fall, in this case, late fall manure. The red one is also late fall manure with instinct. We had it in 2016, but that was actually coming off a soybean year, so not showing that data. But as we look at this, in every year, we see statistically significant difference. You see a difference in letter between fall manure and spring manure. So there was about a 38 bushel per acre increase in corn yield with the spring manure compared to the late fall manure application. Okay, so about 38 bushel per acre average over those 3 years, with a high in 2018 of about, I think, 50 to 60 bushel increased corn yield with that spring manure. Okay, so again, we might not be able to do it on all of our acres because of concerns with compaction and so forth, but could we do it on a little bit of our acres? Maybe get better nitrogen utilization, better, putting that nitrogen from the manure, more of that into the crop, increasing our corn yield, maybe reducing some of the need for commercial fertilizer that some manure producers might put on corn in the year of the corn crop. Okay. Also notice in 2017, 2018, where we did see on an absolute basis in 18 and statistically significant, we saw a little bit of benefit from the instinct with that fall manure compared to the fall manure, the green. So the red bar being slightly greater than the green bar in 2017 and 2018. So that instinct did help us in those 2 years. Okay, so as you think about some of the practices that you might want to implement, specifically maybe cover crops or even tillage, a resource out there that I think could have some really useful decision trees on getting into some of these practices would be the Whole Farm Conservation Best Practices Manual. You can just look for that at the ISU Extension and Outreach store. You can download that PDF for free, and you can order this nice book manual. Still a few left, I think, at the ISU Extension and Outreach store. They're free. You just have to pay for shipping. So I guess that's not free, but you just pay the shipping charge for that. Okay, as we think about those goals out there of a 45% reduction, we are going to need all the available management practices out there. We talked today some about nitrogen management, but we're going to need things like cropping practices, land use, whether that be cover crops or thinking about, perennials in certain areas. They may be helpful. We didn't talk today about the edge of field practices, but things like bioreactors, saturated buffers, wetlands, controlled drainage, drainage water recycling are all practices that may help us intercept that nitrate that's exiting from a tile line, treat that or reuse it in some fashion to reduce downstream nitrate delivery. Okay, as we summarize this, thinking about the 4 R's of nitrogen management, I believe they're important. That's where it starts. Okay, that rate is very important, impacts nitrogen loss, can impact the profitability of the farmer. The timing of N application can impact N loss and crop yield. With our commercial fertilizer, we didn't see much difference, really no difference, in N loss or crop yield difference between late fall manure soils 50 degrees and cooling and spring nitrogen application. We did see some decrease N loss when we used split application or side dress. And then with our manure, we definitely saw an impact on N loss and crop yield when we applied that liquid swine manure, injected that liquid swine manure later in the fall on cooler soils, 50 degrees and cooling, and then specifically also on crop yield when we injected that manure in the spring. Cover crops can definitely have the potential to help us reduce N loss. So I think that's the more we can look at, research cover crops and think about how they work into individual systems, I think that's important. And that kind of gets at maybe a guiding principle as much as we can. It may not work for everybody, but keeping living roots on the land a greater percentage of the time with something like cover crops can help us reduce N loss. And with that, I'm hope that something of this was useful. My contact information, or at least my email, mhelmers@iastate.edu. Always happy to have some dialogue, feedback on this, so feel free to reach out. If you're into Twitter, at ISU Ag Water Management, or MGMT, is my Twitter handle. Feel free to reach out in that fashion as well. Thanks a lot, and I hope that, as I said, something of this was useful, and I hope you enjoy your other sessions associated with Crops TV. Thank you very much.